All right, so the next topic that I wanted to discuss is that pH can affect solubility, right? Let's consider the fact that magnesium hydroxide is slightly soluble, right? We know that hydroxides are sparingly soluble, so they're not going to completely dissociate, all right? So that means that we're going to have an equilibrium for this reaction, right? Where mag hydroxide added to water will form an equilibrium with magnesium 2 plus 2 hydroxide ions, okay? Now, if we add acid to this, what happens? Well, that would be like adding H plus. H plus is going to react with those hydroxides. And when that happens, right, that forms water. Okay, so that means that we're going to be weakening this side of our equilibrium, right? We're losing some players on that side, which means that our equilibrium reaction will shift to the products. Okay, well, if it shifts to the products, then that means that more of the mag hydroxide will dissociate, right? Because we've pulled some of this away, which means it will now shift to the right, which means that this will now be more soluble. Okay? Also, recall that some salts can act as acids and bases if they contain the conjugates of weak bases and acids, right? So for example, right, we would have silver phosphate, okay? We add that to water, okay, and it will form, since this is sparingly soluble, right, it will form an equilibrium with 3 silver ions and a phosphate ion, okay? So this phosphate ion, right, this is a conjugate base of a weak acid. Okay. Now, if it's a conjugate base of a weak acid, that means, remember, that weak acid wants to keep, it wants those protons, right? So if I add, right, if I add acid, right, then what's going to happen? It's going to react with the phosphate to form HPO4 2-, right? Because that is a weak acid, so it's not going to want to give up its protons, okay? All right, so that means that if I add an acid to this system, it will shift to the right, okay? On the other hand, right, let's say that I have silver chloride, right? You guys have been working a lot with that in lab. Okay, so you should know that this is going to crash out of solution and form an equilibrium, right? It's going to be sparingly soluble. Ag plus and Cl minus. Okay, now let's say that I add acid to this, right? Well, what happens? Well, the H plus and the Cl minus, right? That's hydrochloric acid. Well, hydrochloric acid is a strong acid, right? Which means that it readily gives up its protons, right? So it will fully dissociate. So adding any H plus isn't really going to affect this equilibrium at all, okay? Because it's not going to do anything with that Cl, okay? Because if it reacts, it will immediately dump that hydrogen away, right? Because it's a strong acid, right? So no shift to equilibrium because Cl minus is the conjugate base of a strong acid. Okay, again, only the weak acids and the weak bases will be able to have any effect on our equilibrium. Okay? All right. Now, our last topic, chapter 16, is going to be precipitation. This will cover slides 10 and 11, so starting with slide 10, right? We have precipitation. Okay, now recall that for regular equilibrium problems, we had a KEQ, right? Our equilibrium constant at equilibrium. And we had a reaction quotient Anybody remember what letter we gave the reaction quotient? Q. Okay, and our reaction quotient, right? When we weren't at equilibrium, right? Usually for our initial concentrations, right? So, similarly, right, we saw that for solubility reactions, we have a solubility product constant, right, at equilibrium. Okay, so just like for our standard equilibrium, right, when we're dealing with our equilibrium in a solubility reaction, right, it has a special designation, okay, but they work the same way, right? And now we will also have a Q, right? And that Q has a special name, okay? It is called our ion product. Okay? It operates just the same as the reaction quotient, except it's going to apply to our solubility reactions. Okay? So, let's say we have reaction for a weakly soluble salt. CaF2. Okay, so calcium fluoride. Calcium fluoride is going to have the dissociation reaction in water of Ca2 plus 2F minus. Right? And all of those species on this side will be aqueous. Okay? So if we were to write our KSP for that particular reaction, right, it would be Ca2 plus at equilibrium times our concentration in fluoride ion at equilibrium squared, right? Because we're using our stoichiometric coefficient, okay? And it will also have an ion product, okay, our QIP, equal to the calcium ions concentration initially, okay, times our fluoride ions concentration initially squared. Again, using our 2 from our stoichiometry, okay? Now, the ion product is actually pretty useful. And it's useful because it can tell us when a precipitate will form. Okay, now, if Q is greater than KSP, right, so if our ion product is greater than, and I'll use the little IP again so that way you know, if our QIP is greater than our KSP, then a precipitate will form until the equilibrium is reestablished. And that should sort of make sense, right? If Q, right, if our initial concentrations are greater than our equilibrium concentrations, then that's like saying I have too many players on this side, which means that my reaction will shift to the left. Well, if it shifts to the left, then that means we'll be forming a whole lot more solid, okay? So that will give us our precipitate. Now, if Q, right, if our ionization product, or sorry, if our ion product is less than our solubility product constant, okay, then no precipitate will form. Right? This will be important for your quiz on Friday, okay? Now let's do an example, okay? This example will be on slide 11. All right, so if we take 100 milliliters of 4.0 times 10 to the negative 4th molar magnesium nitrate, okay, and we add that to 100 milliliters of 2.0 times 10 to the negative 4th molar sodium hydroxide, all right, does a precipitate form? All right, and you'll also need your KSP for mag hydroxide, and that's going to be equal to 8.9 times 10 to the negative 12th. Now, normally for these problems, I will not tell you what precipitate forms, but I'll give you the KSP. So I'll just say KSP is equal to that, and you'll just have to know whatever precipitate forms based on your solubility rules, okay? So, in order to determine if a precipitate forms, right, we'll need to calculate our Q and then compare that to our KSP. So in order to do this, I've written out a couple of steps, right? So the first one is going to be write down your reactions, okay? Now your reaction for this process, right, will be to take magnesium nitrate, we will add that to sodium hydroxide, all right, and we will form, based on our solubility rules, we know that magnesium hydroxide will crash out, right, because it's not going to be soluble, okay? Mag hydroxide is MgOH2, that will be a solid. And then we will also have our sodium nitrate. All nitrate salts are soluble, so that will get an aqueous designation, all right? The next thing that you'll want to make sure is that you've balanced. Right, so I had 2 hydroxides that I needed, which pushes me up to 2 sodium nitrates. And I think we're balanced now. All right. The next thing that you're going to want to do is eliminate any spectator ions. All right. Essentially, what I'm asking you to do is to write your net ionic equation. Okay. So I know that my aqueous salts, all nitrate salts are soluble. All sodium salts are going to be soluble. All right. And all nitrates are going to be soluble, but my mag hydroxide is not. So splitting them up into all their ions, I have magnesium 2 plus NO3 well, 2 NO3 minus, okay, plus 2 sodium plus 2 hydroxide minus goes to mag hydroxide, right? It's not soluble, plus 2 sodium plus 2 nitrate. All right? If it appears, just like what we did in Gen Chem 1, if it appears on the left and the right, we're going to get rid of it. Nitrates appear on the left and the right. My sodiums also appear on the left and the right. So therefore, those species will be canceled. Okay? And then we can write our net ionic equation as Mg2 plus aqueous plus 2 hydroxide aqueous goes to MgOH2 solid. All right? That would be my net ionic equation. Okay? All right, so once I've got my net ionic equation, right, then step 3 is to get the moles of each reagent or reactant. Okay? Now, our reactants are going to be magnesium and the hydroxide. Okay? So, we have N is equal to M times V, right? Because I've got the moles, or sorry, I've got the molarities and I've got the volumes of each. Okay? So, I can calculate my moles of magnesium nitrate, NO3 2, is equal to 4.0 times 10 to the negative 4th molarity times 0.1 liters, that's 100 milliliters, which is equal to 4.0 times 10 to the negative 5th moles. Okay, so that would be moles of the magnesium nitrate. Now, the moles of magnesium are 1 to 1. Okay, so that means that my moles of magnesium 2 plus is also equal to 4.0 times 10 to the negative 5th moles. If I were trying to get my moles of nitrate ion, which I'm not interested in, but if I were, right, it would have to be 2 times this. Okay, just remember that you have to keep track of your stoichiometry even within your molecular conversions. Okay, now similarly, we would also see that we get moles of hydroxide ion are equal to 2.0 times 10 to the negative 5th moles. All right. Once we've got that, then we can get our molarities by using our total volume. Okay, so we're going to get our total volume, and then we're going to calculate our new molarities, right? Those will be our new concentrations initially. Okay? And again, when we're calculating Q, we're going to need our initial concentrations. All right, now, our total volume shouldn't be too hard. Okay, it's going to be 100 milliliters plus 100 milliliters. Which is equal to 0.2 liters, okay, or 200 milliliters. All right, with that new volume, right, then I can get my concentration of Mg2 plus initially by taking my number of moles, right, and dividing that by my total volume, okay? Here, it will be 4.0 times 10 to the negative 5th divided by 0.2 liters, which will equal 2.0 times 10 to the negative 5th molar. Okay? Similarly, we can get our concentration of OH minus initially by saying 2.0 times 10 to the negative 5th moles divided by 0.2 liters, which is equal to 1.0 times 10 to the negative 5th molar. All right? Now, the next step, again, I'm just walking you guys through this, but really, it's a whole lot simpler if you just sort of think about what you're doing, right? Because I know that I need to get my Q, right? And I know that my Q, right, my ion product is going to be equal to my concentration of Mg2 plus initially times my concentration in OH minus squared initially, right? So we're going to write our QIP, okay? Now my ion product is equal to this, and then I can evaluate, okay? So step 6 is going to be to solve and compare with my KSP, okay? So QIP is equal to 2.0 times 10 to the negative fifth times 1.0 times 10 to the negative fifth squared, which is equal to 2.0 times 10 to the negative 12th, all right, which means that QIP is less than my KSP, and if it's less, then that means that it's going to favor the products, right? It's going to favor being dissociated, okay? So that means that we have no precipitate formed. All right, and with that, that will conclude everything for chapter 16. All right, now, the quiz on Friday will include a little bit of material from the next chapter. All right, so make sure that you watch the next couple of videos that appear before the quiz that appears in Canvas. Okay, so make sure that you watch those videos because a little bit of that material from our next chapter will also appear on the quiz. All right, so with that, shoot me any questions, all right, via email if you have them, and I'll be happy to help. Thank you.